In this video, I will give a summary of a very recent paper on learning strides in convolutional neural networks by Riyad Rachid et al. So, strides are a basic mechanism for downsampling representations in a CNN, which jointly convolve inputs and finite impulse response filters and downsample the output. They provide several benefits. First, they act as a bottleneck that forces features to focus on information relevant to the task. Second, pooling layers such as low-pass filters improve shift variance. And thirdly, a reduced resolution implies a reduced number of floating point operations and a higher receptive field in the subsequent layers. So the problem is that the integer nature of strides only allows for drastic reductions in resolution. For example, a two-dimensional convolution with a stride of 2 reduces the dimension of its inputs by 75%. Graham in 2014 proposed fractional max pooling that allows for fractional strides, allowing for integration of more downsampling layers into the network. Similarly, Ripple et al. In 2015 introduced spectral pooling which, by cropping its inputs in the Fourier domain, performs downsampling with fractional strides while emphasizing lower frequencies. While fractional strides give more flexibility in designing downsampling layers, they increase the size of an already gigantic search space. As strides are hyperparameters, finding the best combination requires cross-validation or architecture search. This rapidly becomes infeasible as the number of configurations grow exponentially with the number of downsampling layers. So a few people proposed a neural network that learns the resizing function for natural images, but the scaling factor, that is the strides, still required cross-validation. So the nature of strides as hyperparameters rather than trainable parameters hinders the discovery of convolutional architectures, and learning strides by backpropagation would unlock a virtually infinite search space. Authors proposed DiffStride, which is a novel downsampling layer that allows spectral pooling to learn its strides through backpropagation. The learnable box W is parameterized by the shape of the input, a smoothness factor R, and the strides. They designed this mask W as the outer product between two differentiable one-dimensional masking functions, one along the horizontal axis and one along the vertical axis. The same can be seen in the bottom right corner of the figure. And this is the pseudocode for the DiffStride layer. Authors performed DiffStride on two experiments. The first experiment was audio classification and the second was image classification. These are the results from audio classification on single task and multitask audio classifications. They were acoustic scene classification, bird song detection, music instrument, music pitch, and speech commands classification. These are the results from image classification. They applied DiffStride on resonant 18, comparing the original strided convolutions with the DiffStride convolutions. They randomly sampled 6 striding configurations for the 3 shortcut blocks of resonant 18, each stride being sampled in 1,3, with 2 being the configuration of the original resonate of He et al. In year 2016. So DiffStride is overall much more robust to poor choices of strides, converging consistently to a high accuracy on the 3 datasets, with a variance over initializations that is lower by an order of magnitude. This shows that backpropagation allows DiffStride to find better configuration during training. Uh, in the future, the authors will extend the scope of applications of DiffStride to one-dimensional and three-dimensional architectures. And also, learning strides by backpropagation opens new avenues in designing adaptive convolutional architectures such as multi-scale models that would learn to operate at various scales in parallel by using independent branches with separate instances of this right. Thank you.